Now, we've looked at, well, you should know the Lorentz force law. One of the most important laws we've got is F equals B Q V, often written like this. That's the vector way of writing it. I'll put the little strokes underneath for the vectors. Now, cross product, that force is going to be perpendicular. Now, what I wanted to think a little bit about though was just show you, have a little think about where F equals BIL came from, because we've got this force on a moving charge in a magnetic field. Where does that come from? So what's the force once we get a bit of a current flowing? So this is actually an effect when a current flows in a wire when it's in a magnetic field. So that's my magnetic field. Crosses indicating it goes that way into the page. And we've got this wire, and what we're doing is we're saying if a current flows, which way will the force go? Okay, so if we make the current flow that way, all right, that was similar to the one we did when we were looking at the V equals BLV equation. What we can say is, obviously we've got this length and we've got this formula, but I just want to see where it was going to come from. F equals BQV, all right? Now that's the magnetic force. Can we make any substitutions there going to help us with that? This is velocity, all right? Now, what we can do is we can say, well, velocity for the wires, these electrons flowing in this wire, are going to be the length of the wire divided by the time it takes, t. And current would be charge divided by t. All right, how much charge passes in that time? Same t, so for the length. So that whole length there is the length of the wire. Can we make substitutions there? Well, we can. We could say then that F equals B, and instead of velocity, we can, instead of just putting velocity, we can put L over T. Okay, and charge, we can make a substitution for charge, right? We've said that current equals charge over T. So if current equals charge over T, then charge equals IT. And we just cancel, and we've got F equals B I L. So that's the force. Now that actually ends up being, if you just put a current through a wire in a magnetic field, it's going to experience a force, and that's the motor effect. The problem, of course, is that when you actually have a alternator and you're spinning it, you make a voltage, then if you let a current flows, this motor force, or this force, back force I call it with the alternator, will tend to make it more difficult for that alternator to spin. But I just wanted to derive that. We're done.